Every modern AI agent faces the exact same engineering trade-off. Autonomy requires access, and access requires containment. The more capable the model, the thicker the walls we build around it. But the Pi coding agent, built by Arundel Works, ignores this rule entirely. It is a highly capable, model-agnostic coding assistant that ships with zero out-of-the-box security containment. To understand why, we have to look at the standard primitives of agent architecture. Most frameworks build in strict handling for the file system, code execution, context, memory, sandboxing, and permissions. Pi intentionally strikes sandboxes and built-in permissions from its runtime entirely. In its default configuration, this creates an immediate risk profile classified under OWASP LLM06 as excessive agency. The agent has the exact same permissions as the user running the command line interface. You see this clearly in Pi's built-in bash tool. There is no command allow list. The schema accepts any string the model decides to generate. When that tool executes, it spawns the command directly on the host machine, inheriting the full parent environment. There is no isolated Docker container or read-only volume attached by the runtime itself. The industry standard is to solve this by building heavy internal safety graphs, writing in-process guardrails, and enforcing strict node-to-node verification. Pi rejects all of that. This absence of guardrails is a meticulously designed feature. By stripping out internal security, Pi proves a specific architectural thesis. An agent harness should function strictly as a neutral turn engine, not a permanent prison. We can see how this neutrality is achieved by looking at the structure of the monorepo. The codebase is fractured into a clean 3-layer seam. The top layer is packages/AI. Its sole responsibility is multi-provider transport and streaming. It knows how to talk to Anthropic, OpenAI, and others, but it knows nothing about tools or logic. The bottom layer is packages/coding agent. This is the host product. It supplies the command line interface, the concrete tools like bash and read, and the user telemetry. Sandwiched between them is packages/agent. This is the runtime loop itself. It talks to no external APIs directly, and it owns zero tools. One iteration of this engine, defined in run loop, follows a strict sequence. It drains any queued steering messages from the user, streams exactly one assistant response from the AI layer, and extracts whatever tool calls the model requested. Then it dispatches those tools to the host, appends the execution results to the transcript, and checks a series of host-provided lifecycle hooks before starting over. If you grep the runtime codebase for iteration limits, you will find 0 hits. There is no max iterations variable here. The loop is structurally unbounded. It only stops naturally when the model reaches convergence, meaning the AI returns a response with 0 tool calls, indicating it believes the task is complete. The only other ways to break the loop require explicit host intervention. Either a tool batch passes a specific terminate flag, or the host triggers a should stop after turn hook. Because the engine is completely agnostic to what it executes, it performs no loop detection and no repeat call deduplication. If a model hallucinates and issues the exact same file system edit 20 times in a row, the runtime will blindly dispatch that request 20 times. Delegating iteration budgets and behavioral loop detection to the host application maintains the purity of the runtime layer. The loop simply observes and acts. When the model does ask to act, the runtime has to figure out how to satisfy the request without owning any tools itself. It uses a linear namescan. The runtime checks the requested tool name against a registry supplied by the host application during the session initialization, passing the arguments blindly. By default, if the model requests multiple tools in a single turn, Pi executes them in parallel to maximize output speed. Individual tools can override this behavior. If a tool definition carries a sequential flag, the runtime honors it, ensuring state-dependent operations execute in order. This brings us back to the security paradox. If the loop executes parallel bash commands blindly on the host file system, how is the user's machine protected? Protection relies entirely on a single extension seam, the before tool call lifecycle hook. In the standard installation, this hook ships without a default handler. It is an empty socket that lets all execution traffic pass through untouched. Users write extensions to plug into this socket. The Gondolin micro-VM extension drops into this seam, rerouting bash requests from the host into an isolated Linux virtual machine. Tools can also modify the agent mid-turn. A tool execution can return an added toolnames array in its payload, registering entirely new capabilities for the next loop iteration without requiring a restart. By stripping out internal protections and providing explicit extension hooks instead, Pi ensures its security posture scales precisely to the limits of the external container the host chooses to provide. Managing execution is only half the problem. The agent also needs memory to maintain context over long, unbounded sessions. This visualization shows Pi's memory model. It relies on flat, static text files. The resource loader simply walks the directory tree, tracing upward from the current working directory to the project root, looking for markdown files like agents.md. There are no internal vector databases or fact stores here. This introduces a distinct zombie memory risk. Stale project instructions written in those files persist and re-inject into the prompt every single turn until a user manually edits them. To keep the LLM's context window from overflowing, Pi relies on a host-invoked compaction pass. Between turns, the host checks the transcript against an absolute token reserve limit. If it breaches the threshold, the system triggers a secondary LLM call to summarize the early transcript, replacing raw tool outputs with a compacted narrative. Knowledge of specific tools is handled similarly through progressive disclosure. Pi injects a minimal index of skill.md files into the system prompt, instructing the model to use the read tool to fetch the full file contents only when it deems a task relevant. This memory and tool design reveals Pi's most controversial stance, a complete, deliberate rejection of the Model Context Protocol. MCP has rapidly become the ecosystem standard. It provides a structured RPC layer, allowing agents to seamlessly plug into external memory tiers, databases, and third-party tools through standard WebSockets. Pi's architecture ignores it entirely. The repository contains zero MCP transport logic. The counter-argument is that providing raw bash execution, combined with flat markdown reads, accomplishes the exact same goals at a fraction of the token cost. Pi sacrifices standardized ecosystem interoperability to preserve its token economy strictly for the model's core reasoning. Look across the landscape of AI frameworks, and the assumption is that the harness must grow heavier as the tasks grow harder. More nodes, more complex graphs, more rigid internal rules. This table outlines Pi's contrasting philosophy, design to delete. The theory states that harness features exist solely to patch over things a model cannot yet do alone. When the model improves, the scaffolding should be removed. Explicit compaction passes only exist because of strict context window limits. As models achieve effectively infinite context and flawless in-context recall, that feature becomes a literal waste of compute and gets deleted. The progressive disclosure of skill files exists because models struggle to hold massive codebases in working memory. When zero-shot repository recall improves, the injected index layer becomes a pass-through. Even host-level verification hooks are temporary. When a model can reliably test and verify its own behavior without external gating, the need for programmatic testing loops inside the agent harness disappears. Under this model, the ultimate trajectory of agent architecture is shrinkage. As capability rises, the required engineering around the model decreases. This resolves the paradox of the naked harness. Pi ships with excessive agency and delegates sandboxing to the host because building permanent, heavily engineered infrastructure for temporary model limitations is a structural mistake. Frameworks that enforce rigid execution graphs and deep internal security measures solve today's problems, but risk trapping the next generation of models inside slow, highly opinionated software prisons. By keeping the runtime strictly neutral, owning zero tools, and pushing limits and security to the host, Pi ensures the framework survives. The job of the ideal harness is to simply get out of the AI's way.